Beneath the quiet streets of southern Europe, the ground has begun to move again. Not with fire and not with ash, but with slow uplift, shallow earthquakes, and gases rising through ancient volcanic rock. This is Campi Flegrei, a hidden caldera near Naples, watched by scientists because its silence is not the same as sleep. In this documentary, the story moves from Europe's surface into the deeper layers of one of its most closely monitored volcanic systems. Like this video, subscribe to the channel and settle in for the quiet science beneath the restless ground. Across Europe, the land appears settled and ancient. Mountain chains rise in long grey folds above forests and rivers. Plains stretch outward through France, Germany, Poland, and Ukraine. The Atlantic Ocean presses against the western edge of the continent with slow tides and winter storms. To the south, the Mediterranean Sea lies between Europe and Africa, enclosed by curved coastlines that have shifted for millions of years. The region holds traces of glaciers, vanished oceans, compressed seabeds, and broken crust. Much of this landscape changes so slowly that movement becomes almost invisible within a human lifetime. Southern Europe rests beside one of the most active geological regions on Earth. The Mediterranean basin forms a meeting place between large sections of the planet's outer shell. These sections, called tectonic plates, move gradually across the hotter material beneath them. The motion is measured in only a few centimeters each year. Even so, over immense periods of time, entire seas narrow, mountains rise, and deep fractures open through rock. The Mediterranean itself preserves evidence of these long changes. Parts of its floor contain dense oceanic crust, formed beneath ancient seas. Other regions contain lighter continental crust, shaped through repeated compression and stretching. Islands emerge from underwater ridges. Deep basins collect layers of sediment carried from rivers and coastal erosion. Salt deposits remain from periods when sections of the sea partly dried and then filled again. Beneath the calm surface of the water, faults and volcanic systems continue to reshape the region. Italy extends into the centre of this basin like a narrow stone bridge between mountains and sea. The Italian peninsula curves through the Mediterranean along zones where the crust bends, fractures, and sinks downward into the mantle below. Along its western side, volcanic regions appear at intervals beside the Tyrrhenian Sea. Some form steep islands rising directly from deep water. Others spread across low coastal plains where towns and cities now stand. Farther north, the Alps form a broad barrier of uplifted rock across Central Europe. Snow gathers along high ridges. Rivers descend through valleys carved by ancient ice. South of these mountains, the land lowers into plains and coastal basins shaped by volcanic activity and tectonic stress. The Apennine Mountains run down the length of Italy like a spine, separating the Adriatic coast from the Tyrrhenian side. Earthquakes occur regularly through these mountains as sections of crust continue to adjust under pressure. The Tyrrhenian Sea occupies a special place within this wider system. Compared with older parts of the Mediterranean, this basin is relatively young. Its crust has stretched and thinned through time. Underwater volcanoes rise from its floor. Heat escapes upward through fractures beneath the sea. Geological surveys reveal areas where molten rock once moved closer to the surface. The basin remains active today, though much of its motion occurs beyond direct human sight. Along the coast near Naples, the landscape changes character again. Hills curve around bays and harbours. Ancient lava flows harden into dark rock beneath roads and buildings. Volcanic ash enriches the soil, supporting vineyards, orchards, and dense vegetation. The climate remains mild through much of the year, shaped by warm seas and moist air moving inland. Millions of people live across this region, often surrounded by reminders of earlier eruptions preserved in stone and sediment. Mount Vesuvius rises east of Naples as the most visible volcano in the area. Its slopes hold forests, farms, and towns climbing gradually upward toward the crater. Historical eruptions from Vesuvius are widely known because of their destructive effects on nearby Roman settlements nearly 2,000 years ago. Ash buried entire communities beneath thick volcanic deposits, preserving buildings, streets, and human remains beneath hardened layers of pumice and dust. Since then, the volcano has erupted many times, though with varying intensity. Yet Vesuvius represents only one part of a larger volcanic region. West of Naples lies a broader and less immediately visible structure known as Campi Flegrei, often translated as the Phlegraean Fields. The name reflects the ancient appearance of smoking ground and heated vents scattered across the landscape. Unlike a steep volcanic cone, Campi Flegrei spreads outward as a large caldera. A caldera forms when a volcanic system empties enough magma during a major eruption that the ground above collapses inward. The result is a vast depression shaped by ancient explosions and structural failure. Today, much of this caldera blends into ordinary urban surroundings. Roads cross old crater rims, buildings stand above buried volcanic layers. Coastal districts occupy land shaped by repeated uplift and sinking. The city of Pozzuoli sits partly within the caldera itself. Harbours extend into water that has risen and fallen relative to the land over centuries. Roman columns near the shoreline preserve visible marks left by marine organisms, showing that the ground has moved vertically through time. The wider region appears peaceful during most days. Fishing boats move through calm water. Ferries cross the bay beneath changing light. Streets remain crowded with traffic and daily activity. Yet scientific instruments placed across the landscape record constant motion beneath this surface stability. Satellites measure tiny shifts in elevation. Seismic stations detect small earthquakes below towns and coastlines. Gas sensors monitor changing chemistry near volcanic vents. Researchers study patterns that unfold slowly across years and decades. Observations indicate that the ground within Campi Flegrei has risen significantly during several periods of modern monitoring. The process is known as bradyseism, meaning slow movement of the ground upward or downward. Parts of the region have lifted by several meters across recorded history. At other times, the land gradually sinks again. These changes affect buildings, roads, and harbours, but they also reveal movement occurring deeper within the volcanic system. The outer landscape of southern Europe therefore contains signs of deeper forces hidden below rock, water, and cities. The Mediterranean coast appears stable on ordinary days, yet the crust beneath it continues to shift under persistent stress. Heat moves upward from below the surface. Old volcanic structures remain active in subtle ways. The visible world above ground becomes a thin outer layer over a much larger system, extending downward into darkness, pressure, and slow geological motion. Beneath the broad surface of southern Europe, the crust belongs to a slow and crowded tectonic setting. The word tectonic refers to the movement and deformation of the outer shell of Earth. This shell is not a single unbroken skin. It is divided into large and smaller plates that move over the hotter, weaker mantle below. In the Mediterranean region, these plates do not meet in a simple line. They press, bend, rotate, tear, and sink in patterns that have developed over many millions of years. The largest nearby plates are the African plate and the Eurasian plate. Africa moves generally northward relative to Europe. The motion is slow, often only a few centimeters each year, but it is persistent. Over geological time, this movement has narrowed ancient ocean basins and built mountain chains. The Alps, the Apennines, the Dinarids, and other ranges around the Mediterranean record this long collision. Layers that once lay beneath shallow seas have been lifted high above the surface, folded into ridges and broken by faults. A fault is a fracture in rock where movement has occurred. In southern Europe, faults form networks rather than single clean breaks. Some faults are compressed as crust is shortened. Others stretch apart as basins open. Some slide sideways as blocks of crust shift past one another. These motions create earthquakes when stored stress is released suddenly. Many earthquakes are small and pass unnoticed by most people. Larger ones can damage towns and reshape slopes, especially where old buildings stand on soft sediment or unstable hillsides. Italy sits within this complex boundary zone. It is not simply pushed from one side. Its crust is affected by the northward motion of Africa, by the resistance of Europe, by the sinking of older oceanic slabs, and by the opening of the Tyrrhenian region to the west. A slab is a section of cold, dense lithosphere that descends into the mantle at a convergent boundary. Lithosphere means the rigid outer layer made of crust and uppermost mantle. As a slab sinks, it can pull nearby crust, change stress fields, and help produce volcanic activity above or behind it. The Apennine Mountains show the effect of these forces. Along parts of the range, the crust has been compressed in earlier stages, then stretched during later stages. This mixture creates a landscape of ridges, basins, and active faults. Mountain fronts rise beside valleys filled with sediment. Rivers follow weak zones in the rock. Earthquakes occur at shallow depths where the crust is brittle enough to break. The pattern is uneven, because the crust contains inherited structures from earlier geological events. To the west of the Apennines, the Tyrrhenian Sea marks an area where the crust has thinned. Geological evidence indicates that this basin opened as the region behind the Apennine chain stretched. Extension means pulling apart. When crust extends, it becomes thinner and hotter material from below may rise closer to the surface. This does not mean that molten rock fills the whole region. It means that heat flow may increase and fractures may become pathways for magma and fluid. In the Tyrrhenian area, this stretching is linked with volcanic provinces along the western side of Italy. The African plate does not move beneath Europe as one smooth surface everywhere. Older fragments of oceanic crust have descended in some areas, while other parts have become tangled with continental blocks. The central Mediterranean includes small crustal blocks and microplates, which are smaller moving pieces within the larger plate boundary. Their motion can differ from the main plates around them. This helps explain why earthquakes and volcanoes appear in curved belts, rather than along a single straight line. One important part of the regional frame is subduction. Subduction occurs when one plate sinks beneath another into the mantle. Around the Mediterranean, subduction has shifted position through time. In some places, the descending slab has rolled backward, meaning the hinge of the sinking plate has migrated. This rollback can stretch the crust behind the volcanic arc and create space for basins to form. It can also influence where magma is generated and where it rises. The process is gradual and can remain active even when surface movement appears quiet. Volcanism in this setting is tied to both melting and movement. Rock in the mantle can begin to melt when water and other volatile substances are released from a descending slab. Volatile substances are materials that move easily as gases or fluids under geological conditions. Their presence lowers the temperature at which mantle rock begins to melt. The resulting magma may rise through the crust if pathways exist. Some magma stalls and cools underground, some reaches the surface and erupts. Some remains as heat and chemical change within deep rock. The Italian peninsula lies near several of these volcanic and tectonic influences. The exact geometry below the surface is studied with earthquake waves, gravity measurements, heat flow observations, rock chemistry, and satellite data. These methods do not reveal a perfectly simple image. They show a region shaped by curved slabs, stretched crust, old faults, and zones of hot material. Observations indicate that the volcanic systems of Western Italy are connected to this wider tectonic environment. It remains uncertain in many places exactly how magma bodies, faults, and fluids connect at depth. The Mediterranean boundary also changes through time. A fault that is active in one period may become less active later. A basin may stop opening while another zone begins to deform. Volcanic activity may migrate as the stress field and mantle conditions evolve. This long evolution leaves rocks from many stages stacked close together. Ancient marine limestone can stand near young volcanic ash. Deep crustal fragments can lie beneath modern cities. The region becomes a layered record of compression, extension, collapse, and heating. At the scale of daily life, this motion is nearly still. A few centimeters each year cannot be seen by standing on a road or watching a coastline. At the scale of instruments, it becomes measurable. Satellite systems detect gradual deformation across wide regions. Seismic networks locate earthquakes and show where brittle rock is breaking. Geological mapping traces old fault lines across mountains and valleys. Chemical studies of volcanic rocks reveal sources deep below the surface. Each method adds one part to the picture. The tectonic frame beneath southern Europe is therefore a slow arrangement of forces rather than a single event. Africa continues to move relative to Europe. Slabs have sunk and shifted below the Mediterranean. The Apennines continue to adjust. The Tyrrhenian region preserves the effects of stretching and heat. Western Italy carries the volcanic response to these deeper processes. This outer tectonic setting forms the broad mechanical background in which hidden volcanic systems remain active, measured and incompletely understood. Around the central Mediterranean, volcanic activity appears as a scattered belt rather than a continuous wall of fire. The region contains islands, coastal cones, submerged vents, calderas, and old volcanic fields now softened by erosion and settlement. Their shapes differ because they form in different parts of the same broad tectonic setting. Some rise where magma reaches the surface through narrow vents. Some spread outward from repeated eruptions across wide fields. Some collapse into large depressions after powerful eruptions empty underground storage zones. Together, they show how heat and melt reach the surface through a crust that has been compressed, stretched, and broken through time. The volcanic belt of Italy is one of the clearest parts of this pattern. It follows much of the western side of the peninsula, from central Italy toward the islands of the south. In some places, old volcanic lakes fill round basins left by explosive eruptions and collapse. In others, dark lava flows form low plateaus or steep cliffs above the sea. Volcanic rocks appear in Rome's surrounding hills, in the Alban Hills southeast of the city, in the Campanian region around Naples, and across island chains in the Tyrrhenian Sea. These areas are not identical, but their distribution reflects the deeper structure of the Mediterranean boundary. Volcanoes form when magma, gas, and heat find pathways through the crust. Magma is molten or partly molten rock beneath the surface. When it erupts, it becomes lava if it flows, or ash and pumice if it fragments explosively. The style depends on composition, gas content, temperature, and the shape of the pathway. Some magma flows easily and builds broad shields or dark sheets of lava. Other magma is rich in silica and gas, making it thicker and more likely to erupt explosively. In Italy, many volcanic systems have produced explosive deposits, including ash, pumice, and pyroclastic flows. A pyroclastic flow is a fast-moving mixture of hot gas and volcanic particles that travels along the ground. The central Mediterranean contains several active or recently active volcanic systems. Stromboli, in the Aeolian Islands, is known for frequent small explosions from an island cone rising above the sea. Etna, on Sicily, is one of the most active volcanoes in the world, with eruptions that often involve lava fountains, ash, and flows from vents on its flanks and summit. Volcano, also in the Aeolian Islands, has fumaroles and a history of explosive eruptions. Vesuvius, near Naples, is a steep stratovolcano, a layered cone built from lava and explosive deposits. Campi Flegrei, west of Naples, is a broad caldera rather than a single cone. Each system occupies its own structural setting, but all belong to a region where mantle melting, crustal fractures, and volatile-rich magma interact. Volcanic islands of the Tyrrhenian Sea show another part of the belt. The Aeolian Islands form an arc north of Sicily, with volcanic centres arranged above a zone influenced by subduction processes. Their rocks contain chemical traces of fluids released from descending lithosphere. These fluids change the melting conditions in the mantle and contribute to magma generation. The islands rise from the seafloor, so most of their volume lies underwater. Their visible peaks are only the upper parts of the larger volcanic structures built through repeated eruptions. Farther beneath the sea, submerged volcanoes and volcanic ridges continue the pattern. Some are extinct, meaning they no longer show evidence of present activity. Others may retain heat or hydrothermal circulation. Hydrothermal circulation means the movement of hot water through cracks in rock. These systems can alter minerals, release gases, and create deposits on the seafloor. Because they lie underwater, their activity is harder to observe directly. Researchers use seafloor mapping, water chemistry, earthquake monitoring, and rock sampling to understand them. On land, volcanic fields can look quiet for long periods. Erosion lowers cones. Vegetation covers ash layers. Towns grow around crater rims and lakes. The absence of eruption over centuries does not always mean that a system is extinct. Scientists distinguish between extinct, dormant, and active volcanoes based on geological history, present signals, and the likelihood that magma or heat remains. Dormant means quiet at the surface but capable of future activity. Active means there is evidence of current or recent unrest, eruption, heat flow, gas release, or seismic activity. These terms are useful, though natural systems do not always fit neatly into categories. The volcanic belt is also marked by differences in scale. Some eruptions release small amounts of lava or ash. Others produce broad deposits that reshape entire landscapes. Caldera eruptions are among the largest because they can involve large volumes of magma and collapse of the surface. The central Mediterranean has records of eruptions that dispersed ash across wide areas, including the Campanian ignimbrite from Campi Flegrei about 39,000 years ago. An ignimbrite is a deposit formed mainly from pyroclastic flows. This event left volcanic material across parts of Italy and beyond, though its exact environmental effects remain a subject of continuing study. The belt does not behave as one connected machine with every volcano changing together. Each volcanic center has its own storage zones, pathways, rock chemistry, and stress conditions. Activity at one volcano does not automatically mean activity at another. Still, the systems share a regional background. They occupy crusts shaped by the same broad plate motions and mantle processes. This shared setting explains why volcanic centers are clustered along certain zones, rather than spread evenly across Europe. Monitoring across the belt varies from place to place. Highly active volcanoes such as Etna, Stromboli, Vesuvius, and Campi Flegrei are watched with networks of instruments. These include seismometers, ground deformation sensors, gas stations, thermal cameras, and satellite measurements. The purpose is to identify changes in behavior. A change may include more earthquakes, faster ground movement, altered gas chemistry, or increased heat. Such changes do not always lead to eruption. They show that conditions within the volcanic system are shifting. The Mediterranean volcanic belt therefore forms an outer ring of context around the hidden system near Naples. It is a region where the surface records many paths for heat rising through damaged crust. Some volcanoes stand as visible cones, others are low fields, islands, or underwater structures. Some release gas quietly for centuries. Others erupt in sudden episodes separated by long stillness. The belt remains a measured, studied, and living expression of the deeper forces beneath southern Europe. Southern Italy's volcanic coast lies where mountains, sea, and fractured crust meet in a narrow and densely settled region. The land around Naples curves around the Bay of Naples and the Gulf of Pozzuoli, forming a coastline of headlands, low plains, islands, and steep volcanic slopes. The area appears open and bright at the surface, with water reflecting the sky and towns spreading across hills. Beneath this outer calm, the coast records repeated eruptions, ground movement, and long interaction between volcanic rock and the sea. The city of Naples stands between two major volcanic neighbours. To the east rises Vesuvius, a steep cone built from alternating layers of lava, ash, and broken volcanic material. To the west spreads Campi Flegrei, a broad caldera whose shape is less obvious because much of it is occupied by towns, low hills, craters, and coastal water. Between them lies an urban region that has grown over centuries on volcanic deposits. Roads, harbours, churches, railways, and homes rest on ground made by earlier eruptions. The coast itself is not a simple edge between land and water. It is a moving boundary shaped by sea level change, tectonic motion, eruption, erosion, and ground deformation. Some parts of the shoreline consist of soft tuff, which is hardened volcanic ash. Tuff can be cut by waves into cliffs and caves. Other areas contain loose ash, pumice, and sediment washed down from slopes. Bays and inlets occupy low areas formed by collapse or erosion. Small islands stand offshore as pieces of the same volcanic landscape, separated from the mainland by water. The Bay of Naples opens toward the Tyrrhenian Sea. Its eastern side is dominated by Vesuvius and the volcanic deposits around it. Its western side is shaped by Campi Flegrei and by older volcanic structures extending toward the islands of Procida and Ischia. The sea connects these systems visually, but each has its own history and behavior. The water also hides part of the volcanic record. Some vents, faults, and deposits lie beneath the bay, where surveys must rely on seafloor mapping, sediment cores, and geophysical measurements. Vesuvius is the most recognizable volcanic form along the coast. Its cone rises from the remains of an older volcanic structure known as Monte Somma. The present summit sits within the older rim, showing that the volcano has changed shape through collapse and rebuilding. Historical records describe eruptions that sent ash into the air, produced lava flows, and generated dangerous currents of hot gas and debris. The eruption in the 1st century of the Common Era buried Pompeii, Herculaneum, and nearby settlements. Later eruptions continued until the 20th century, after which Vesuvius entered a quiet period. The slopes around Vesuvius are heavily inhabited. Towns occupy old lava flows and ash deposits. Fertile volcanic soil supports agriculture, while roads and buildings extend close to the volcano's base. The presence of many people increases concern because volcanic hazard is not only a matter of eruption size, it also depends on exposure, building strength, evacuation routes, warning time, and public response. Scientific monitoring around Vesuvius is therefore closely tied to civil protection planning. Observations track earthquakes, gas, ground motion, and other signs of unrest. West of Naples, the coast lowers and broadens into the Campi Flegrei area. Here the volcanic form is harder to recognize because the caldera is wide and partly flooded. Instead of one high cone, the region contains many small craters, tuff rings, domes, and depressions. A tuff ring forms when explosive eruptions scatter ash around a vent, often where magma interacts with water. Some craters are dry and built over. Others contain lakes or low wetlands. Some have been altered by quarrying, roads, or urban growth. Pozzuoli lies near the centre of this coastal volcanic field. Its harbour faces the Gulf of Pozzuoli, a sheltered body of water within the larger Bay of Naples region. The town has long been affected by bradyseism, the slow rising and sinking of the ground. In different periods, the shoreline has shifted relative to buildings and docks. The ancient marketplace, often called the Serapeum, preserves columns marked by marine borers, showing that the site once sank low enough for seawater to cover part of the structure, then rose again. These marks provide a visible record of vertical movement along the coast. The Solfatara crater sits inland from Pozzuoli as one of the most familiar surface expressions of Campi Flegrei. It is a shallow volcanic depression with steaming vents, warm ground, and mineral deposits. Fumaroles release gases and water vapour from the heated system below. The area has been studied for centuries because it shows how a caldera can remain active without erupting. Gas release and hot ground do not by themselves mean an eruption is occurring. They show that heat and fluids continue to move through the shallow crust. Farther west and south, coastal features continue the volcanic pattern. The island of Procida contains low volcanic forms and layered deposits. Ischia, larger and more rugged, shows evidence of volcanic activity, uplift, landslides, and hydrothermal systems. Although Ischia is separate from Campi Flegrei, it belongs to the same broad volcanic province along the Tyrrhenian margin. Its cliffs and hot springs reveal the continuing influence of heat beneath the region. The island's geology adds another layer to the volcanic coast, where land, water, and deep heat remain closely connected. The human surface of this coast is dense and continuous. Naples and its surrounding towns form one of the most populated volcanic regions in the world. Buildings cover ancient deposits. Rail lines cross caldera floors. Harbours operate near moving shorelines. Archaeological sites stand beside modern streets. The landscape carries both ordinary life and geological memory. A wall may be built from tuff cut from nearby hills. A road may follow the edge of an old crater. A garden may grow in soil made from ash. Scientific study of this coast must therefore account for both natural processes and human presence. Mapping cannot treat the area as an empty volcanic field. Instruments must be placed among streets, buildings, ports, and protected sites. Measurements must separate local effects from broader deformation. Gas surveys must consider both volcanic emissions and human sources. Earthquake records must be interpreted within a complex structure of faults, caldera margins, and shallow hydrothermal zones. Southern Italy's volcanic coast is a surface where deep forces reach the edge of daily life. The region contains visible cones, hidden caldera walls, ancient craters, steaming ground, and shorelines that have moved up and down through time. It is not defined by a single volcano alone. It is a coastal volcanic province shaped by repeated eruptions, crustal stress, seawater, and settlement. Its outer form is made of bays, slopes, islands, roads, and towns resting above rock that remains warm, fractured, and closely watched. Campi Flegrei spreads west of Naples as a volcanic landscape that does not rise into one clear summit. Its surface is low, uneven, and lived in. Streets pass through old craters. Homes stand on gentle slopes made of ash and tuff. Roads cross depressions that once held vents or lakes. The caldera is present as a broad shape rather than a single mountain. Its rim is partly hidden by later eruptions, erosion, buildings, and the sea. The result is a volcanic field that blends with ordinary coastal life while still preserving many signs of its origin. A caldera is a large volcanic depression formed when the ground collapses after a major eruption removes support from below. At Campi Flegrei, this depression has been modified by later activity. Smaller eruptions have built cones, rings, and domes within the larger structure. Some vents formed on land, others formed near water or beneath shallow marine areas. The surface therefore carries many separate volcanic features, each belonging to a different moment in the system's history. Their forms are softened, but they remain readable in the curves of hills, lakes, bays, and low rims. The name Campi Flegrei means burning fields, a phrase linked to the visible heat and gas that have long marked the area. In several places, steam and volcanic gases rise from the ground. Mineral crusts form around vents where gases cool and react with air and rock. Soil may be warm to the touch in restricted areas. These features are not eruptions. They are surface expressions of heat and fluid moving through fractures below. Their presence shows that the volcanic system is not cold or completely sealed. One of the most visible surface areas is Solfatara, a shallow crater with pale ground, steaming fumaroles, and altered rock. A fumarole is an opening that releases volcanic gas and water vapor. The gases include water vapor, carbon dioxide, hydrogen sulfide, and other compounds in smaller amounts. Hydrogen sulfide can produce a strong sulfur smell. Around fumaroles, minerals may stain the ground yellow, white, or grey. The rock becomes weak where hot acidic fluids have changed its minerals. This alteration can make the ground fragile in places, which is why access to such zones is controlled. The Solfatara crater is not the whole caldera, but it provides a clear example of how Campi Flegrei expresses activity at the surface. The floor is broad and relatively flat. Steaming vents cluster in certain zones rather than everywhere. The edges of the crater rise gently and connect to surrounding urban districts. The site demonstrates that heat and gas can remain active long after an eruption has ended. It also shows how hydrothermal activity can concentrate near fractures and permeable layers. Nearby, the town of Pozzuoli stands as one of the most important places for observing surface movement. The streets, harbour, and ancient structures lie within the zone of greatest recorded vertical change. The Roman marketplace near the coast, often called the Serapeum, contains columns marked by marine organisms. These markings show that the land sank below sea level for a time and later rose again. The columns become a simple visible record of bradycism, the slow uplift and subsidence of the ground. The word bradycism means slow shaking or slow movement, but in this region it mainly refers to gradual vertical motion. The coastline around Pozzuoli shows how volcanic ground interacts with the sea. Harbour structures, sea walls, beaches, and archaeological remains occupy land that has changed elevation repeatedly. When the ground rises, the shoreline may shift outward, and harbour depths may decrease. When the ground sinks, seawater may move farther inland or cover older structures. These changes are usually slow, but they matter in a densely built coastal town. They also provide evidence that pressure and fluid movement beneath the surface can deform a wide area. Other craters and volcanic features are scattered across the caldera. Some contain lakes, such as Lake Averno, which occupies a volcanic depression with steep green slopes. Lake Averno is surrounded by deposits from explosive eruptions that formed when magma interacted with groundwater or surface water. The lake itself appears calm, but its circular shape records a violent origin. Nearby landforms preserve tuff rings and ash layers, though vegetation and construction have softened their outlines. Astroni is another large crater within the caldera, now partly covered by woodland. Its enclosed form shows how volcanic depressions can become sheltered landscapes after activity ends. Trees grow across the floor and slopes. Wildlife occupies the quiet interior. Yet the shape remains volcanic, with walls that mark the boundary of an eruption center. The contrast between living forest and explosive origin is common in older volcanic terrains, where time allows ecosystems to settle over deposits made in sudden events. The caldera surface also includes Monte Nuovo, a small volcanic cone formed during the eruption of the 16th century. Its name means new mountain. This eruption is the most recent known eruption of Campi Flegrei. It built a cone over several days and altered the local landscape near the coast. The event followed a period of ground uplift and unrest. Today, Monte Nuovo is covered by vegetation and paths, but its youthful form remains clear compared with older, more eroded features. It shows that new volcanic landforms can appear within the caldera rather than only along its edge. Urban settlement covers much of the region. Pozzuoli, Boccoli, Quarto, Naples suburbs, and other communities occupy ground shaped by volcanic deposits. Buildings stand on tuff, ash, lava domes, and reworked sediment. In places, roads curve around crater rims without making the volcanic structure obvious. Construction has cut into hillsides and exposed layers of ash and pumice. Some old quarries reveal bedding that records repeated eruptions. These exposures help geologists understand the sequence of events, though many are hidden or altered by development. Surface signs at Campi Flegrei therefore appear in many forms. They include steaming vents, warm ground, altered minerals, crater lakes, circular depressions, young cones, uplifted shorelines, and ancient ruins marked by changing sea levels. None of these signs alone defines the state of the volcano. Together, they show that the caldera is a broad, active volcanic system with heat, fluids, deformation, and past eruptions distributed across a complex surface. The visible land is not a simple cover over a single vent. It is a mosaic of old and recent features that record how the hidden system has reached the surface through many pathways. Across Campi Flegrei, the ground does not remain fixed in height. It rises and sinks in measured cycles that can last for years, decades, or centuries. This movement is one of the most important surface observations in the caldera. It is not a sudden eruption, and it is not the same as an earthquake. It is a slow deformation of the land, spread across a wide area, with the strongest motion usually centered near Pozzuoli. The movement is called bradyseism, a term used for gradual vertical motion of the ground in volcanic regions. The deformation field is the pattern made by this movement across the surface. A field, in this sense, means the way a measurable change is distributed from place to place. At Campi Flegrei, instruments show that uplift is not equal everywhere. Some locations rise faster than others. Some areas lie near the center of motion, while more distant areas move less. The pattern is broad and roughly centered within the caldera, but it is shaped by local faults, rock layers, coastline geometry, and the structure left by earlier eruptions. Pozzuoli has recorded some of the largest changes. Historical evidence shows repeated phases of subsidence and uplift. Ancient coastal structures give a long view of these changes, while modern instruments provide precise measurements. During parts of the 20th century, the ground rose by several meters in episodes that affected buildings and infrastructure. One major period of uplift occurred in the early 1970s. Another occurred in the early 1980s. These events were accompanied by earthquake swarms and concern among authorities, leading to evacuations in parts of Pozzuoli during the early 1980s. Modern monitoring has continued to record uplift in the caldera. Global navigation satellite systems measure the position of fixed stations on the ground. These systems use signals from satellites to detect movement in 3 dimensions. Radar satellites also measure deformation from space by comparing repeated images of the same surface. This method can detect small changes in elevation over wide areas. Leveling surveys, which use precise ground-based measurements along routes, have provided additional records over time. Together, these methods show that Campi Flegrei has experienced renewed uplift during recent decades. The shape of uplift matters. If pressure increases beneath the ground, the surface may bulge upward. The center of uplift can indicate the approximate area where pressure changes are strongest, although it does not reveal a simple empty chamber or single source. At Campi Flegrei, scientists test different models to explain the observed deformation. Some models involve movement of magma at depth. Others involve pressurized fluids in the hydrothermal system. Some include both. Observations indicate that pressure changes beneath the caldera are real. It remains uncertain how much of each uplift phase is caused by magma, by hot fluids, or by interaction between them. The ground responds because rock is not perfectly rigid. In the shallow crust, rock can bend slightly, fracture, compact, or open along cracks. Volcanic deposits may be layered and uneven, with ash, tuff, lava, and altered zones having different strength. Hot fluids can weaken rock by changing its minerals. Faults can guide movement or divide the caldera into blocks that respond differently. Because of this complexity, the surface deformation field does not act like a simple, smooth sheet. It contains broad trends and local variations. At the coast, uplift has visible effects. When land rises relative to the sea, the waterline appears to fall against harbour walls and ancient structures. Docks may become shallower. Rocks that were once below water may emerge. When land sinks, the sea returns higher against the same surfaces. These changes have been observed historically around Pozzuoli. They make the movement easier to imagine because the sea provides a nearly level reference surface, yet the cause remains underground. where pressure and temperature change within a system that cannot be seen directly. Deformation also affects buildings and roads. Slow movement can tilt surfaces, open cracks, and stress foundations. Much of the movement may be gentle across a single structure, but uneven deformation can create damage, especially where old masonry is already weakened. Earthquakes associated with uplift can add further stress. In a dense urban area, even slow geological motion becomes a practical issue. Monitoring, therefore, serves both scientific and public safety purposes. The timing of uplift is not constant. Some periods show faster movement, other periods slow or pause. Subsidence can follow uplift, though not always in a simple reversal. This irregularity is part of the challenge. A rising ground surface means the system is changing, but it does not automatically mean an eruption will occur. Past unrest at Campi Flegrei has not always led to eruption. The most recent known eruption, Monte Nuovo in the 16th century, did follow notable uplift. Modern episodes have produced significant deformation and earthquakes without eruption. This difference shows why scientists avoid treating uplift alone as a prediction. The deformation field is studied together with other signals. Earthquake locations can show where rock is breaking as the ground rises. Gas emissions can show whether hot fluids are changing in amount or composition. Temperature measurements can indicate changes in heat flow near vents. The most useful interpretation comes from combining these observations. Ground uplift may reflect pressure increase, but the nature of that pressure is better understood when compared with seismic, chemical, and thermal data. Models of deformation use mathematics and physical assumptions to estimate the depth, size, and pressure of possible sources. These models are useful, but they are simplified. The crust beneath a caldera is not uniform. It contains old intrusions, fractured zones, hydrothermal reservoirs, and altered rock. A model that fits the surface movement may not be unique. Different underground arrangements can sometimes produce similar uplift at the surface. For this reason, results are interpreted with caution. Observations indicate that the present deformation of Campi Flegrei is part of a long pattern of unrest in a living caldera. The ground has moved before, and it continues to move now. The movement is measured carefully because it reflects pressure changes beneath a populated volcanic field. It remains uncertain exactly how deep processes divide between magma and fluids during each episode. What is known is that the surface rises in a coherent pattern, strongest near the central caldera area, and that this movement is one of the clearest outward signs of activity beneath Campi Flegrei. Within the Campi Flegrei caldera, earthquakes form another measured layer of activity. They are usually shallow, small, and clustered in time. Many are too weak to be felt across the wider region, yet instruments record them clearly. Some are strong enough to wake residents, crack plaster, or cause concern in neighborhoods close to the center of unrest. These earthquakes do not occur randomly. They tend to appear in patterns that reflect stress, pressure, fractures, and the movement of fluids beneath the ground. An earthquake begins when rock breaks or slips along a fracture. In volcanic areas, this can happen when pressure changes underground deform the crust. As the ground rises, rocks are stretched, bent, and compressed. If the stress becomes greater than the strength of the rock, it breaks. The released energy travels outward as seismic waves. Seismic waves are vibrations that move through the earth and are detected by instruments called seismometers. By measuring arrival times and wave shapes, scientists estimate the location, depth, and size of each event. At Campi Flegrei, many earthquakes occur at shallow depths within the upper few kilometers of crust. This matters because shallow earthquakes can be felt more strongly near their source than deeper events of similar size. The energy has less distance to travel before reaching the surface. Shallow events also show that brittle rock close to the surface is responding to deformation and pressure changes. The exact depth of each earthquake has some uncertainty, but the overall pattern places much of the activity in the shallow caldera structure. Earthquake swarms are common in volcanic systems. A swarm is a sequence of many earthquakes occurring close together in space and time, without one single main shock followed by a simple aftershock pattern. At Campi Flegrei, swarms can include dozens, hundreds, or more small events during periods of unrest. Their timing may match phases of faster uplift. This connection suggests that rising pressure and rock failure are linked. The relationship is not exact, because the crust responds unevenly and fluids can move through fractures in complicated ways. Some earthquakes occur near known zones of fumarolic activity and altered ground. These areas may contain hot fluids, steam, and gas moving through cracks. When fluid pressure increases in a fracture, it can reduce friction and make slipping easier. When hot acidic fluids weaken minerals, rock may fracture more readily. This does not mean that every earthquake is caused directly by moving fluid. It means that the shallow crust contains both mechanical stress and hydrothermal processes, and the two can influence each other. The size of volcanic earthquakes is measured by magnitude, which describes the energy released. Most events at Campi Flegrei are small. Magnitudes near 0 or 1 may be recorded only by sensitive instruments. Events around magnitude 3 may be felt locally. Larger events are less common but can be important because of the dense population and shallow depths. Even moderate shaking can affect old masonry, narrow streets, and buildings already stressed by ground deformation. For this reason, earthquake monitoring is not only a scientific task, it is also part of public safety work. Seismic networks around the caldera have become more detailed over time. Stations are placed across the region to record ground motion continuously. Some instruments are installed in urban settings, where traffic, construction, waves, and human activity create background noise. Scientists must separate volcanic earthquakes from these other vibrations. Careful processing allows them to identify small events and map their locations. The resulting earthquake catalogues show how activity changes through days, months, and years. The location of earthquakes can outline active fractures. When many events form a cluster, they may show where rock is breaking repeatedly. When they align along a plane or band, they may suggest a fault or crack system. In a caldera, these patterns can be difficult to interpret because old collapse structures, vent zones, and buried faults overlap. The caldera has been broken and refilled many times. Its crust contains layers of ash, tuff, lava, and intrusions. Each layer has different strength and permeability. Permeability means the ability of rock to let fluids pass through its pores and cracks. Earthquake waves also carry information about the material they pass through. Some studies use the speed and attenuation of seismic waves to infer whether rocks are fractured, hot, or fluid-rich. Attenuation means the weakening of waves as they travel. Hot rock, gas, and fluids can change how waves move. These methods help build images of the subsurface, though they are not simple photographs. They are interpretations based on physical measurements. Observations indicate zones of altered, fractured, and heated rock beneath parts of the caldera. The exact arrangement remains under study. Not all seismic signals are ordinary brittle earthquakes. Volcanic regions can also produce low-frequency events, tremor, or signals linked to fluid movement. Tremor is a more continuous vibration rather than a single break. At Campi Flegrei, the main concern in many unrest periods has been shallow volcano-tectonic earthquakes, which are brittle failures associated with stress. Other signal types are monitored because they may reveal changes in fluids or gas pathways. Their interpretation depends on waveform shape, duration, frequency, and location. The relationship between earthquakes and eruption remains careful and limited. Earthquake swarms can occur before eruptions at some volcanoes because magma or gas forces rock to crack while moving upward. Yet swarms can also occur without eruption, especially in hydrothermal or deforming caldera systems. Campi Flegrei has experienced strong unrest with many earthquakes and uplift without erupting in modern times. Observations therefore indicate unrest and stress release, not a direct prediction. It remains uncertain which seismic patterns would mark a clear transition toward eruption without support from other evidence. For residents, earthquakes are often the most direct sign of unrest. Ground uplift may be measured by instruments, and gas chemistry may be studied in laboratories, but shaking is felt immediately. A small event beneath a town can make windows rattle and furniture move. Repeated swarms can create anxiety even when damage is limited. This human response becomes part of the broader volcanic risk, because public communication must explain what is known, what is being monitored, and what remains uncertain. In the inner pattern of the caldera, earthquakes show where the rock is adjusting to pressure. They mark shallow failure within a heated or fractured volcanic structure. They cluster, migrate, pause, and return as stress changes. They are linked to uplift and fluids, but not in a perfectly predictable way. The earthquake zone of Campi Flegrei is therefore a sensitive layer between the visible surface and the deeper system below, recording small breaks in rock as the caldera continues to move. At the surface of Campi Flegrei, gas and heat appear through vents, warm ground, altered minerals, and diffuse emissions from soil. These signs are quieter than earthquakes and less visible than rising land, but they form one of the clearest links between the shallow surface and the hot system below. Gas moves where fractures, pores, and permeable layers allow it to pass upward. Heat travels with steam, hot water, and gases, changing the ground along the way. The result is a surface that breathes slowly through selected openings rather than evenly across the whole caldera. The most familiar gas vents are fumaroles. A fumarole is an opening where volcanic gases and water vapor escape from heated rock. At Campi Flegrei, fumaroles occur especially around Solfatara and nearby Pisciarelli. They release water vapor, carbon dioxide, hydrogen sulfide, sulfur dioxide in smaller amounts, and other gases that scientists measure carefully. The exact mixture can change over time. These changes are important because gas chemistry can reflect temperature, pressure, fluid pathways, and possible input from deeper sources. Water vapor is often the most visible part of a fumarole plume. It condenses in cooler air and forms white steam. Much of this vapor may come from groundwater heated by the volcanic system. Rain and surface water seep into porous rock, descend through cracks, become heated, and rise again as steam or hot water. This circulation can continue for long periods without eruption. It creates a hydrothermal system, which is a network of hot water, steam, and altered rock above deeper heat sources. Carbon dioxide is especially important at Campi Flegrei. It is colourless and odourless, and it can move not only through vents but also diffusely through soil. Carbon dioxide is heavier than air, so in low or poorly ventilated areas it can accumulate near the ground. Scientists measure its flux, meaning the amount passing through a surface over time. High carbon dioxide flux can indicate strong degassing from below, although it can also be influenced by rainfall, soil conditions, pressure changes, and biological activity. Careful measurements across many locations help separate local variations from broader volcanic signals. Hydrogen sulfide gives some fumarolic areas a sulfur smell. It can oxidize near the surface and contribute to the formation of yellow sulfur minerals. In the presence of water and oxygen, sulfur gases can produce acidic fluids. These fluids react with volcanic rock and alter its minerals. Hard rock may become soft, pale, and clay-rich. Iron-bearing minerals may change color. Silica and sulfate minerals may form crusts around vents. Over time, this chemical alteration weakens the ground and changes how fluids move through it. Gas temperature is another monitored property. Fumarole temperatures can show changes in the shallow hydrothermal system. A rise in temperature may reflect greater heat flow, a change in steam supply, or a shift in pathways. A stable temperature may suggest steady circulation. Yet the meaning is not always simple. Surface vents can be affected by rainwater, seasonal conditions, blockage by minerals, and changes in shallow fractures. For this reason, temperature data are interpreted together with gas chemistry, ground deformation, and seismic activity. At Piciarelli, vigorous gas and mud emissions have drawn close scientific attention. The area lies near Solfatara and contains bubbling pools, steaming ground, and strong carbon dioxide release. Mud pools form where gases rise through water and fine sediment, stirring the surface. They are not lava. They are part of a hot, gas-rich hydrothermal environment. Their behavior can change as gas flow, rainfall, and shallow pathways change. Observations of such areas help scientists understand how pressure is released near the surface. Heat also moves through the ground by conduction and convection. Conduction is the transfer of heat through solid material. Convection is the movement of heat by fluids such as water, steam, or gas. In volcanic areas, convection often dominates where cracks and porous layers allow hot fluids to circulate. At Campi Flegrei, the distribution of warm ground is uneven because permeability is uneven. Some zones vent strongly. Nearby areas may be cooler because the pathways do not connect directly to the surface. The chemistry of gases can provide clues about deeper processes. Ratios between carbon dioxide, water vapor, sulfur species, helium, and other components may indicate whether gas is mainly from shallow boiling water, deeper magma, or a mixture of sources. Helium isotopes are sometimes used to trace mantle or magmatic contributions. An isotope is a form of an element with a different number of neutrons in its atoms. Such measurements require careful sampling and laboratory analysis. Observations indicate that gases at Campi Flegrei include components linked to deep volcanic sources, as well as shallow hydrothermal circulation. It remains uncertain how changes in gas chemistry translate into short-term eruption likelihood. Pressure changes below the surface can affect gas flow. If fluids become more pressurized, they may open new pathways or increase flow through existing ones. If minerals seal cracks, pressure can build until fractures reopen. This sealing and breaking can create cycles of gas release, ground deformation, and small earthquakes. In altered volcanic rock, minerals may precipitate from hot fluids and clog pores. Later, stress or pressure can break the sealed zones. The system then becomes a changing network rather than a fixed set of pipes. Gas emissions also interact with the atmosphere near the ground. Wind disperses plumes. Rain can dissolve gases and change soil chemistry. Calm weather can allow carbon dioxide to gather in hollows. Vegetation may be stressed in areas of high heat or gas concentration. These effects are local, but they help identify zones of strong degassing. Remote sensing can sometimes detect thermal anomalies, while ground teams make direct measurements at vents and soil sites. The surface release of gas is not the same as a direct view of magma. Gas may separate from magma at depth, pass through hot rock, mix with groundwater, react chemically, and emerge changed at the surface. Some signals may be delayed or filtered by the hydrothermal system. This makes interpretation difficult. A change at a fumarole may reflect a shallow blockage opening, a pressure pulse from deeper fluids, increased boiling, or new gas input from depth. Scientists compare many observations to reduce uncertainty. At Campi Flegrei, gas and heat pathways form a living surface network. Fumaroles release steam and acidic gases. Soil emits carbon dioxide through invisible roots. Mud pools stir where gas rises through wet sediment. Warm ground and altered minerals mark places where heat has changed rock. These signs show that the caldera remains connected to deep heat, but they do not provide a simple forecast by themselves. They are part of a broader pattern of unrest, measured slowly and carefully, as the hidden system releases energy through the shallow crust. Beneath the fumaroles, warm ground, and gas vents of Campi Flegrei lies a hydrothermal reservoir. It is not a hollow lake or a single underground chamber. It is a body of heated rock, water, steam, gas, and minerals occupying pores and fractures within the shallow crust. Rainwater and seawater can enter the ground through cracks and permeable layers. Heat from deeper volcanic sources warms these fluids. As they circulate, they dissolve minerals, react with rock, separate into steam and liquid, and move upward where pathways allow. A hydrothermal system is a natural circulation system driven by heat. At Campi Flegrei, it sits above deeper magmatic heat and within volcanic deposits that have been broken, altered, and sealed many times. The reservoir is therefore uneven. Some zones may contain liquid water under pressure. Others may contain steam, gas, or mixtures of both. Some pathways are open and allow fluids to move. Others are partly blocked by minerals deposited from hot water. This changing structure helps explain why surface emissions can vary without a surface eruption. Pressure is central to the behavior of this shallow reservoir. Water under pressure can remain liquid at temperatures higher than its normal boiling point at the surface. When pressure decreases, some of that water may flash into steam. This expansion can increase stress in surrounding rock. If pressure builds inside sealed fractures, the rock may bend or break. If a pathway opens, gas and steam may escape more easily. The system can therefore shift between storage and release, with changes recorded as ground deformation, earthquakes, or altered gas flow. The reservoir is also shaped by boiling. Boiling does not occur everywhere at once. It depends on temperature, pressure, and depth. In one part of the system, hot water may remain liquid because pressure is high. In another part, closer to the surface or near an open fracture, water may boil and produce steam. Steam carries heat and volatile substances upward. As it rises and cools, it may condense back into water. This repeated boiling and condensation transfers energy through the shallow crust. The fluids are chemically active. Hot water can dissolve elements from volcanic rock, including silica, sulfur, chlorine, iron, and other components. As conditions change, these elements may precipitate as new minerals. Precipitation means that dissolved material leaves the fluid and forms solid crystals. These minerals can line fractures, fill pores, and create seals. Sealing reduces permeability, the ability of rock to transmit fluids. When permeability decreases, pressure may rise behind the sealed zone. Later fracturing can reopen pathways, allowing stored gas or steam to move again. This sealing and reopening may contribute to the unrest pattern at Campi Flegrei. A sealed hydrothermal system can transmit pressure to the surrounding rock. The ground may rise as pressure increases. Small earthquakes may occur as brittle rock breaks. Gas emissions may change if pathways close or open. Observations indicate that the hydrothermal reservoir plays a major role in shallow activity. It remains uncertain how much each unrest episode is driven by fluid pressure alone, and how much is influenced by new heat or gas from deeper magma. The reservoir does not exist separately from the rocks around it. Volcanic deposits at Campi Flegrei include ash, tuff, lava, breccia, and intrusive bodies cooled underground. Breccia is rock made of broken fragments cemented together. These materials have different strength and different capacity to hold or transmit fluid. Tuff may be porous in some layers and sealed in others. Lava may be dense but fractured. Altered rock may become clay-rich and weak. Intrusive rock may form harder bodies that redirect fluid movement. The reservoir follows this complex architecture. Clay minerals are especially important in altered volcanic systems. When hot acidic fluids react with rock, they can form soft clay-rich zones. These zones may trap fluids because clay has low permeability. They may also deform differently from stronger rock. A clay-rich cap can act as a barrier, keeping pressure below it. If pressure rises enough, the cap may fracture. This does not require magma to reach the surface. It can happen within a shallow fluid system. Such behavior is common in hydrothermal areas around volcanoes. Seawater may also influence the shallow reservoir near the coast. Campi Flegrei lies partly beneath land and partly beneath shallow marine areas. Coastal fractures can allow interaction between groundwater and seawater. The chemistry of fluids can carry signs of this mixing. Salt, chlorine, and other dissolved components help scientists identify possible fluid sources. Yet the pathways are complicated because fluids may circulate for long periods and react strongly with rock. Surface samples represent fluids that have passed through many filters before emerging. Temperature at depth is inferred from several kinds of evidence. Direct drilling provides information where boreholes exist, though drilling in active volcanic regions is limited and carefully managed. Gas chemistry can suggest temperatures in deeper parts of the system. Mineral assemblages, which are groups of minerals formed under certain conditions, also record past temperatures and fluid chemistry. Seismic and electrical methods can help image zones that may contain hot fluids or altered rock. Electrical resistivity is useful because water, clay, and hot saline fluids conduct electricity differently from dry rock. The hydrothermal reservoir can store energy without producing an eruption. This is one reason caldera unrest is difficult to interpret. A volcanic system may show uplift, earthquakes, and strong degassing because fluids are pressurizing and moving through the shallow crust. These signals may persist for years. They may intensify and then decline. They may not involve magma rising close to the surface. At the same time, deeper magmatic input can feed heat and gas into the hydrothermal reservoir, changing its pressure and chemistry without immediately erupting. The boundary between hydrothermal unrest and magmatic unrest is therefore not always sharp. At Campi Flegrei, the shallow reservoir acts as a mediator between deep heat and the surface. It receives heat and gases from below. It absorbs rainwater and possibly marine fluids from above and the sides. It changes rock through chemical alteration. It stores pressure in sealed zones. It releases steam, carbon dioxide, and other gases through vents and soil. It can deform the ground and help trigger shallow earthquakes when pressure changes. It is a restless but hidden inner layer, close enough to affect towns and vents, yet complex enough that its exact state remains only partly known. Below the hydrothermal reservoir, the upper crust of Campi Flegrei becomes a deeper framework of fractured volcanic rock, buried intrusions, old collapse structures, and layers changed by heat. This region is still shallow in geological terms, but it lies beyond direct sight. It is known through earthquake waves, drilling records, gravity measurements, electrical studies, rock samples, and the patterns seen at the surface. The upper crust is not a uniform block. It is a complicated body made from many eruptions, collapses, intrusions, and long periods of alteration. The crust beneath the caldera carries memory of the events that formed it. When large eruptions remove magma from depth, the ground above can fail and sink. This collapse breaks the crust into blocks and rings of faults. Later eruptions may fill depressions with ash, lava, and debris. Magma may rise but stop underground, cooling as intrusive rock. Hydrothermal fluids may move through cracks and change minerals. Each process leaves a structure that can guide later movement. The present upper crust is therefore both a container and a record. At Campi Flegrei, the caldera structure includes faults related to collapse and later deformation. Ring faults are fractures that can form around the edge of a collapsing volcanic depression. They are not always clean circles, and many may be buried or partly erased by later deposits. Within the caldera, smaller faults and cracks divide the rock into blocks. These fractures can influence where earthquakes occur, where gas rises, and where the ground deforms. Some may act as pathways. Others may act as barriers if sealed by minerals. The rocks themselves vary strongly with depth and location. Nearer the surface, volcanic deposits can include loose ash, pumice, tuff, and reworked sediment. Deeper down, these materials may become more compact. Tuff can harden as ash particles become cemented together. Lava bodies and intrusive rocks may form stronger layers. Breccias may mark zones where rock broke during collapse or explosions. Altered zones may be rich in clay, sulfates, silica, and iron minerals. These differences matter because each rock type responds differently to stress and fluid pressure. Seismic waves help reveal this structure. When an earthquake occurs, waves travel through the crust. Their speed changes depending on rock type, temperature, fractures, and fluid content. Faster waves may indicate denser or colder rock. Slower waves may suggest hotter, fractured, or fluid-rich zones. Scientists use many earthquakes and many recording stations to build three-dimensional images. These images are called tomographic models, meaning they're reconstructed from waves crossing the underground region from different directions. They do not show perfect detail, but they provide important clues. Electrical and electromagnetic methods add another view. Rocks conduct electricity differently depending on water, dissolved salts, clay minerals, temperature, and melt. Dry solid rock usually resists electrical flow more strongly. Hot saline fluids and clay-rich altered rock conduct more easily. By measuring natural or induced electrical signals, researchers can infer zones of high or low resistivity. Resistivity means resistance to electrical current. In volcanic areas, low resistivity often points to fluids or altered minerals, though interpretation requires caution because different materials can produce similar signals. Gravity measurements also help. Dense rocks create slightly stronger gravitational pull than less dense rocks. Variations are very small, but sensitive instruments can detect them. In a caldera, gravity patterns may reflect buried intrusions, collapse fill, dense lava bodies, or low-density deposits. Campi Flegrei contains both dense volcanic bodies and lighter altered or fragmented zones. When gravity data are combined with seismic and geological information, they help outline the deeper architecture of the upper crust. The upper crust also contains old magma intrusions. An intrusion forms when magma enters rock underground and cools before reaching the surface. Intrusions can be sheets, dikes, sills, or irregular bodies. A dike cuts across layers, while a sill spreads between layers. These bodies may strengthen parts of the crust and redirect later fractures. They may also remain warm for long periods after emplacement, helping drive hydrothermal circulation at Campi Flegrei. Repeated magmatic activity over thousands of years likely left many such bodies beneath the caldera. Stress moves through this crust unevenly. When pressure rises in a deeper source or in the hydrothermal system, the upper crust bends and fractures according to its weaknesses. Strong blocks may transmit stress over distance. Weak altered zones may deform more easily. Sealed layers may trap fluids. Open fractures may release them. This helps explain why uplift, earthquakes, and gas emissions appear in particular areas rather than everywhere at once. The crust acts less like a simple lid and more like a layered, damaged, partly sealed medium. Temperature increases with depth, though not evenly. Heat comes from the deeper volcanic system and from old intrusions cooling within the crust. Hot fluids carry heat upward along fractures. In some zones, temperature may be high enough to change minerals and weaken rock, even without molten rock nearby. The strength of the upper crust depends on both temperature and fluid pressure. Hot, wet, altered rock can fail differently from cold, dry rock. This makes the mechanical behavior of the caldera difficult to reduce to one simple model. Drilling offers direct but limited information. Boreholes can measure temperature, collect rock samples, and identify fluid conditions at specific points. However, a borehole samples only a narrow path through a very large system. Conditions can vary greatly over short distances in fractured volcanic rock. Drilling in an active caldera also requires careful planning because hot fluids and gas may be encountered. The value of drilling is greatest when combined with geophysical imaging and surface monitoring. The upper crust beneath Campi Flegrei is also influenced by the sea and coastal setting. Parts of the caldera extend beneath water, and marine sediments may cover volcanic deposits offshore. The boundary between land and sea affects groundwater flow, pressure conditions, and the preservation of deposits. Offshore faults and vents may connect with onshore structures, though their exact links are not always clear. Marine surveys provide important information where land-based observations cannot reach. Observations indicate that this upper crust is fractured, altered, and mechanically stressed. It contains pathways for fluids, barriers that can hold pressure, and older structures that shape modern unrest. It remains uncertain exactly how each fracture, intrusion, and altered layer connects across the caldera. The available evidence shows a crust that has been repeatedly opened and sealed, heated and cooled, broken and filled. It forms the deeper container around the shallow hydrothermal system and the outer shell above the hotter regions below. Deeper beneath Campi Flegrei, below the fractured upper crust and the shallow hydrothermal reservoir, the volcanic system reaches the region where magma may be stored, cooled, mixed, or partly connected to rising heat and gas. This region is not a single open cavern filled with liquid rock. Modern volcano science describes magma storage more often as a mouche, a mixture of crystals, melt, gas, and hot solid rock. Some parts may contain more liquid melt. Other parts may be mostly solid but still hot enough to release fluids or be reactivated. The exact shape and state of this storage region remain uncertain because it lies several kilometers below the surface and cannot be observed directly. Magma begins as melted or partly melted rock at depth, but by the time it reaches the crust beneath a caldera, it has usually changed. It may cool and crystallize. It may mix with older magma. It may release gases as pressure decreases. It may react with surrounding rock. It may stop moving and form intrusions. A magma storage region is therefore not only a place where melt sits, it is a changing zone where heat, crystals, gas, and pressure evolve through time. At Campiflegrei, evidence for deeper magmatic material comes from several sources. Volcanic rocks erupted in the past carry chemical information about their origins and storage. Minerals within those rocks preserve clues about temperature, pressure, water content, and the time spent underground before eruption. Seismic studies can identify zones where waves slow down or weaken, which may indicate hot, fractured, or partly molten material. Ground deformation can suggest pressure changes at depth. Gas chemistry can show contributions from deep magmatic sources. None of these observations alone gives a complete image, but together they show that deeper heat and magmatic fluids remain part of the system. The storage region is often described in terms of depth ranges rather than exact boundaries. Some studies suggest shallow sources of pressure at a few kilometers depth, strongly linked to hydrothermal fluids and deformation. Deeper zones, possibly several kilometers farther down, may contain magma bodies or crystal-rich mush. These estimates depend on the method used and the assumptions in each model. Observations indicate that magmatic material exists beneath the caldera system. It remains uncertain how much melt is present at any time, how connected it is, and how easily it can move upward. Gas provides one of the important links between magma storage and surface activity. As magma rises or depressurizes, volatile substances separate from it. Volatile substances include water, carbon dioxide, sulfur compounds, and other materials that can move as fluids or gases. Carbon dioxide can separate from magma at greater depth than water because it becomes less soluble under pressure changes. This means carbon dioxide may travel upward even when magma itself remains deep. At Campiflegrei, measured gases show deep contributions, but they pass through the hydrothermal reservoir before reaching the surface, where their original signal may be modified. The pressure within a magma storage region can change without eruption. New magma may enter from below and add heat and volume. Crystals may form and release gas-rich fluids. Gas may accumulate in pockets or move upward through fractures. Surrounding rock may respond by bending, cracking, or allowing fluids to escape. If pressure is transmitted upward into the hydrothermal system, the surface may rise and earthquakes may occur. This does not require magma to reach the surface. It requires pressure and fluids to affect the overlying crust. The concept of magma mouche helps explain long periods of unrest without eruption. A mouche can remain mostly crystalline and immobile, while still hot enough to feed gas and heat into the surrounding system. If new, hotter magma enters the mouche, it may remelt some crystals or increase the amount of liquid melt. It may also stir older material and change gas release. Whether this leads to eruption depends on many conditions, including melt fraction, gas pressure, pathway strength, crustal stress, and the presence of fractures. At present, These conditions cannot be measured directly with enough certainty to predict a specific outcome from one signal. Past eruptions show that magma has reached the surface at Campi Flegrei many times. The deposits include material from explosive eruptions, lava domes, and smaller vents scattered across the caldera. Chemical differences among these deposits indicate that the magmatic system has changed over time. Some magmas were more evolved, meaning they cooled and crystallized enough to become richer in silica and volatile substances. Such magmas can be more viscous, meaning thicker and less able to flow easily. Viscous magma can trap gas more effectively, increasing the potential for explosive behavior if it reaches shallow levels. This storage region also interacts with the structure of the caldera. Old collapse faults, intrusions, and layered rocks influence where magma or gas may rise. A pathway that existed during one eruption may seal afterward. A later event may open a different path. This is why eruptions within calderas can occur from different vents, rather than always from one central crater. Campi Flegrei's surface record shows many vents across the caldera, reflecting a system where pathways are distributed and change through time. Heat from magma storage keeps the surrounding crust warm. Even when melt does not move upward, heat can be transferred by fluids and conduction. This heat drives the hydrothermal system above. It alters minerals, supports fumaroles, and helps maintain gas emissions. The deeper storage region is therefore connected to surface activity through heat and fluids, even during quiet periods. The connection is indirect, filtered through layers of fractured rock and chemically active water. Scientific imaging of magma beneath calderas is difficult. A low seismic velocity zone may suggest melt, but it can also reflect high temperature, fractures, or fluids. A low electrical resistivity zone may suggest saline fluids, clay, or melt. Ground deformation may fit several possible source shapes. Gas chemistry may carry signals from depth but be changed during ascent. For this reason, scientists compare independent methods and avoid relying on one interpretation. The result is a cautious picture rather than a sharp map. Observations indicate that Campi Flegrei contains a deep heat and magma system capable of feeding unrest. They also indicate that the shallow activity seen at the surface is strongly influenced by fluids and fractured rock above the magma region. It remains uncertain whether current unrest reflects mainly pressure changes in the hydrothermal system, deeper magmatic gas input, small additions of magma, or a combination of these processes. The magma storage region remains the warm inner source of energy and material, partly molten in places, partly crystalline in others, and hidden beneath layers that record its pressure only indirectly. The deeper history of Campi Flegrei is recorded in caldera formation, older eruptions, buried deposits, and repeated collapse. This history lies inward from the present surface because it explains how the present structure came to exist. A caldera does not form from one simple explosion at a single vent. It forms when a volcanic system releases enough magma and fragmented material that the ground above loses support and sinks. The collapse may occur during a large eruption, after it, or in stages connected with the movement of magma and pressure below. At Campi Flegrei, the modern landscape preserves the results of more than one major phase of activity. The oldest parts of this history are difficult to see directly because younger deposits cover much of the region. Erosion, urban construction, marine sediment, and later eruptions have hidden or modified many early layers. Scientists reconstruct the sequence by studying exposed cliffs, drill cores, offshore deposits, mineral chemistry, and ash layers found far from the source. A drill core is a cylinder of rock brought up from underground. It can preserve layers that are not visible at the surface. These layers help build a time order of eruptions and collapses. One of the most important events in the history of Campiflegrae is the Campanian ignimbrite eruption, which occurred about 39,000 years ago. This was a very large explosive eruption that produced widespread deposits of ash and pyroclastic flow material. An ignimbrite is a deposit formed mainly by hot mixtures of gas and volcanic particles that move along the ground. The eruption left traces across large parts of southern Italy and ash layers that can be identified in more distant regions. Its exact volume and environmental effect remain studied, but it is widely recognized as one of the largest volcanic events in Europe during the late Quaternary period. During such an eruption, gas-rich magma fragments into pumice, ash, and hot particles. These materials may rise in a tall eruption column or collapse outward as dense currents. Pyroclastic currents can fill valleys, cross low ridges, and spread across broad areas while still hot. When they settle, they form thick sheets of volcanic material. Some deposits weld together because the particles remain hot enough to deform and stick. Others stay loose or become cemented later, around Campiflegrae. These deposits form part of the foundation beneath later landscapes. Caldera collapse associated with the Campanian ignimbrite helped create a large depression in the region. The exact boundaries and mechanics of this collapse are still studied because the structure is partly buried and partly offshore. Collapse may not have occurred as one clean drop. Blocks of crust can sink unevenly. Ring faults can guide movement. Some areas may subside more than others. Later activity can obscure the original shape. Observations from geology and geophysics indicate a major structural change after this eruption, but details of the collapse geometry remain uncertain. After the Campanian ignimbrite event, volcanic activity continued within and around the caldera. The system did not become inactive. Magma, gas, and heat remained below the region, and later eruptions built new deposits across the collapsed area. These later events modified the caldera floor and created smaller volcanic features. Layers from these eruptions are found in cliffs, quarries, lake basins, and boreholes. Each layer preserves a moment when magma reached the surface or interacted with water and fragmented explosively. Another major eruption occurred about 15,000 years ago and produced the Neapolitan yellow tuff. This eruption is central to the younger history of Campiflegrae. The deposit is widely present around Naples and the caldera, and it has been used as building stone because it is relatively easy to cut when first quarried and hardens with exposure. The Neapolitan yellow tuff eruption also involved caldera collapse, or renewed subsidence within the volcanic system. It reshaped the region and created deposits that still influence the ground beneath modern settlement. The yellow colour of this tuff comes from alteration after deposition. Original volcanic material interacted with water and changed mineral form, producing the distinctive tone. The deposit includes ash and pumice fragments from explosive activity. In many places it became a strong, workable rock. Human use of this tuff connects geological history with the built environment, because parts of Naples and nearby towns include stone formed during this eruption. The same volcanic history that created hazard also supplied material for walls, tunnels, and foundations. Following the Neapolitan yellow tuff eruption, activity became more scattered across the caldera. Smaller eruptions occurred from different vents rather than one central cone. This pattern is typical of many calderas, where magma uses changing pathways through fractured ground. Some eruptions formed tuff rings, some produced cones, some created lava domes or small lava flows. Many involved interaction between magma and water, which can increase explosiveness by turning water rapidly into steam and fragmenting magma and rock. The past several thousand years include eruptions distributed in time and space across Campi Flegrei. Some built craters now occupied by lakes or lowlands. Others left ash layers that are thin but widespread enough to be traced between sites. The eruption of Monte Nuovo in the 16th century is the most recent known eruption. It formed a new cone near the coast after a period of uplift and unrest. This event is important because it occurred in historical time, with records of ground movement and surface change before the eruption. It shows that the caldera can produce new vents after long quiet intervals. The caldera history also includes long pauses. These pauses are not empty in a geological sense. During them, heat continues to move, rocks cool or remain warm, fluids circulate, minerals form, and the ground may deform. A volcanic system can spend far more time in unrest or quiet than in eruption. The rock record is biased toward eruptive events because eruptions leave visible deposits. Non-eruptive processes leave subtler evidence, such as alteration, uplifted shorelines, fractures, and hydrothermal minerals. At Campi Flegrei, both kinds of evidence are needed to understand the system. The inner historical record shows repetition without exact repetition. Large caldera-forming eruptions are rare. Smaller eruptions are more common but still separated by uneven intervals. Vents shift location. Magma composition changes. Water interaction varies depending on groundwater, lakes, sea level, and vent position. Collapse structures influence later pathways, but they do not determine every event in a simple way. The system evolves as each eruption and each period of alteration changes the crust for the next phase. Campi Flegrei's caldera formation history therefore forms a layered inner archive. The Campanian ignimbrite marks a large and ancient collapse-forming phase. The Neapolitan yellow tuff marks a later major reshaping of the caldera. Younger eruptions fill and modify the depression with smaller vents, cones, rings, and deposits. The most recent eruption adds a young cone to a much older structure. Observations indicate a long-lived volcanic system capable of both very large and smaller eruptions. It remains uncertain how future activity would compare with any single past event, because the past provides evidence of possibility, not a fixed pattern of repetition. At the inner core of scientific concern around Campi Flegrei lies hazard assessment. Hazard means the possible dangerous process itself, such as eruption, ash fall, ground shaking, gas release, or ground deformation. Risk includes hazard together with the people, buildings, roads, services, and decisions exposed to it. In a densely populated caldera, assessment must consider both the physical behavior of the volcano and the human landscape above it. The science does not produce certainty. It builds careful estimates from observations, past deposits, models, and the present state of unrest. The first part of hazard assessment is recognizing what the system has done before. Campi Flegrei has produced very large explosive eruptions in the distant past, including caldera-forming events. It has also produced smaller eruptions from scattered vents within the caldera. The most recent eruption, Monte Nuovo in the 16th century, was much smaller than the ancient major eruptions. Yet it still changed the local landscape and followed unrest. This range matters because future activity is not assessed from one past event alone. The record shows several possible styles, from localized explosive activity to larger events, with very different consequences. Eruption size is only one part of hazard. Location matters strongly in a caldera with many possible vents. A new vent could open in one part of the caldera rather than at a fixed summit. This makes planning more difficult than at a cone volcano with a central crater. Scientists study past vent locations, faults, deformation centers, and rock structures to estimate areas where future vents may be more likely. These estimates are probabilistic, meaning they describe relative likelihood rather than certainty. The underground pathway of magma or gas cannot be traced in advance with full confidence. Explosive activity is a central concern because much of the magma in Campi Flegre's history has produced ash, pumice, and pyroclastic material. Pyroclastic currents are among the most dangerous volcanic processes. They are hot mixtures of gas and particles that move along the ground. Even small explosive eruptions can produce local hazards near the vent. Ash clouds can affect breathing, visibility, transport, power systems, water supplies, and buildings. Wet ash becomes heavy and can stress roofs. Fine ash can travel far with wind, though thickness decreases with distance from the source. Ground deformation itself is also a hazard. Rising or sinking land can damage buildings, roads, pipes, harbour structures, and drainage systems. Around Pozzuoli, uplift has already affected daily life during historical and modern unrest. Deformation can occur without eruption, yet still create economic and structural problems. It can also combine with earthquake swarms, increasing stress on vulnerable buildings, because the motion is uneven. Some structures may suffer more than others depending on location and foundation conditions. Earthquake hazard in the caldera differs from large regional tectonic earthquakes, but it remains important. Volcanic earthquakes are often shallow, which can make local shaking noticeable even when magnitude is moderate. Repeated swarms can weaken structures and increase public stress. The dense urban setting means that even localized shaking has practical consequences. Hazard assessment therefore includes expected ground shaking, building vulnerability, and the possibility that unrest may produce many events over time rather than one isolated shock. Gas hazard is more localized but real. Carbon dioxide can accumulate in low areas because it is heavier than air. Hydrogen sulfide and other gases can be harmful at sufficient concentrations. Fumarolic areas and zones of strong soil degassing require careful control. Gas emissions can also affect vegetation and confined spaces. In most parts of the urban region, volcanic gas is not experienced as a constant danger, but specific zones near vents and depressions must be monitored and managed. Hazard assessment identifies these zones through repeated measurement rather than assumption. Hydrothermal explosions are another possible process in heated volcanic areas. They occur when water or steam in the shallow system expands suddenly and fragments surrounding rock. Such explosions can happen without fresh magma reaching the surface. They're usually smaller than magmatic eruptions, but they can be dangerous near the source. The presence of hot fluids, sealed layers, and pressure changes makes this process relevant in fumarolic zones. It remains difficult to forecast exactly because it depends on shallow conditions that can change quickly. The uncertainty in hazard assessment is not a failure of science, it is a property of the system. The subsurface is complex, partly hidden, and constantly changing. Instruments measure deformation, earthquakes, gas, temperature, and other signals. But no single signal gives a complete answer. Uplift may reflect magmatic pressure, hydrothermal pressure, or both. Earthquake swarms may indicate fracturing without eruption. Gas changes may show deeper input or shallow pathway changes. Assessment becomes stronger when several independent observations point toward the same interpretation, but uncertainty remains. Scientists use alert levels to organize interpretation and response. Alert levels do not predict exact events. They describe the state of the volcano based on monitored signs and agreed criteria. A higher level means increased unrest or concern, not certainty of eruption. A lower level does not mean absence of hazard. These levels help authorities, researchers, and the public share a common framework. They also show how scientific uncertainty must be translated into practical categories. Probabilistic hazard maps are used to represent possible impacts. They combine eruption scenarios, vent location estimates, wind patterns, deposit studies, and topography. A scenario is a plausible event used for planning, not a prediction. For ashfall, wind direction and eruption height matter. For pyroclastic currents, terrain and eruption energy matter. For gas, low-lying areas and ventilation matter. For earthquakes, depth and local ground conditions matter. Each map simplifies reality, but it helps organize preparation. The timescale of assessment is also layered. Long-term hazard looks at what the volcano is capable of over centuries or longer. Short-term assessment watches current unrest and asks whether conditions are changing in ways that require action. These two scales can differ. A region may have high long-term volcanic hazard, but show no immediate eruption signs. A period of unrest may raise short-term concern without ending in eruption. Campi Flegrei requires both perspectives because its past shows major capability, while its present behavior includes ongoing deformation, seismicity, and degassing. The word catastrophic in public language often suggests certainty or sudden finality. Scientific assessment uses more careful terms. A large eruption in a densely populated caldera could have severe consequences. A smaller eruption in the wrong location could also be highly disruptive. Non-eruptive unrest can still damage infrastructure and affect communities. Observations indicate that Campi Flegrei is an active caldera under close monitoring. It remains uncertain whether present unrest will lead to eruption, continue without eruption, or change in another measured way. Hazard assessment at Campi Flegrei therefore sits at the center of known danger and measured uncertainty. The past defines possible processes. The present supplies signals of unrest. Models connect observations to likely sources and outcomes. Civil needs require clear thresholds and practical decisions. The science cannot remove uncertainty from a hidden volcanic system, but it can reduce surprise, define plausible hazards, and keep attention fixed on the evidence as the caldera continues to move. Between scientific observation and public action, Campi Flegrei requires a steady exchange of evidence, interpretation, and caution. The volcanic system is measured by instruments, but decisions affect towns, roads, schools, hospitals, ports, and families. Civil protection work begins where monitoring data must be turned into practical choices under uncertainty. The process is not separate from science. It depends on science, but it also includes planning, communication, emergency logistics, and responsibility for people living inside and near the caldera. The scientific side begins with continuous monitoring. Seismic stations record earthquakes. Satellite and ground instruments measure uplift and sinking. Gas sensors track emissions and chemistry. Thermal measurements follow heat at vents and warm ground. Field teams inspect fumaroles, fractures, and altered zones. These observations are gathered over time so that changes can be compared with previous behavior. A single measurement rarely carries meaning by itself. Its importance comes from its relation to trends, thresholds, and other signals. Civil protection agencies need this information in forms that can guide action. Raw data must be checked, interpreted, and explained. A rise in earthquake number may matter more if it occurs with faster uplift and gas change. A gas change may matter more if it is accompanied by pressure signals or new fractures. Scientists therefore work within monitoring networks and advisory structures that combine several kinds of expertise: volcanology, seismology, geodesy, geochemistry, engineering, and risk communication all contribute to the same public problem. Alert levels provide one way to connect science and response. They classify the state of the volcano according to monitored activity and agreed criteria. These levels help officials decide when to increase attention, prepare resources, restrict access, or communicate new guidance. They are not predictions of exact events. They indicate changing conditions. In a caldera such as Campi Flegrei, this distinction is essential because unrest may last for years without eruption. While still requiring serious preparation, emergency planning must account for the shape of the hazard. Campi Flegrei does not have one summit crater that defines all danger. Possible vents may occur in different parts of the caldera. Ash can follow wind. Pyroclastic currents would follow ground and eruption energy. Gas hazards may remain local but dangerous in specific places. Earthquake swarms and ground deformation can affect infrastructure before any eruption. Planning must therefore use zones, scenarios, and flexible procedures rather than one fixed line on a map. Evacuation planning is especially difficult in a dense urban region. Roads must carry large numbers of people. Some routes may pass through areas affected by earthquakes, deformation, traffic congestion, or ash. Ports and rail systems may help, but they also depend on weather, infrastructure condition, and timing. Hospitals, elderly residents, people with disabilities, and schools require special arrangements. Scientific information helps define when such plans may need activation. But the movement of people is a social and logistical task as much as a geological one. Communication is part of the emergency science interface. Information must be accurate without being obscure. It must avoid false certainty and avoid unnecessary alarm. The public needs to understand that unrest is real, that monitoring is active, and that uncertainty remains. Calm communication does not mean minimizing the hazard. It means stating what observations show and what they do not show. In a volcanic crisis, confusing language can cause harm, either by increasing panic or by weakening trust. Trust depends on consistency. When authorities explain why a level changes, why access is restricted, or why no immediate eruption is expected despite unrest, the reasoning must be clear. Repeated updates can help people understand long periods of activity. Campi Flegrei can produce many earthquakes and continued uplift without an eruption occurring. This creates a difficult communication environment because people may become tired of alerts or doubtful of warnings. Scientific and civil institutions must continue to explain that non-eruptive unrest can still be meaningful and that preparedness remains necessary. Urban planning also belongs to the interface between science and protection. The location of buildings, roads, emergency centres, and critical services affects future risk. In a long-inhabited volcanic region, many settlements already exist in hazardous zones. Science can identify areas of greater exposure, but changing land use is slow and often limited by history, economics, and culture. Even so, hazard maps can guide building standards, infrastructure reinforcement, access planning, and education. Reducing risk does not require waiting for a crisis. It can occur through steady adjustments over many years. Exercises and drills turn plans into tested procedures. A written evacuation plan is not the same as a working evacuation. Drills reveal problems in routes, communication, timing, coordination, and public understanding. They also help institutions practice roles before pressure rises. In Campi Flegrei, where warning signs may be ambiguous, practice procedures become especially important. They allow action to begin from a known structure rather than from improvisation alone. Scientific uncertainty must be included in decision-making rather than hidden from it. A clear forecast of eruption time, place, and size is not available for Campi Flegrei. The subsurface is too complex, and present signals can have more than one cause. Authorities therefore work with probabilities, scenarios, and thresholds. A decision to prepare or evacuate may need to occur before certainty exists, because waiting for certainty can mean waiting too long. This is one of the hardest parts of volcanic risk management. At the same time, early action has costs. Evacuation disrupts lives, work, healthcare, education, and local economies. Restrictions can affect businesses and movement. False alarms can reduce future trust. These costs do not erase the need for safety, but they show why decisions must be grounded in the best available evidence. The interface between science and civil protection balances the danger of acting too late with the consequences of acting too early. The balance changes as observations change. International scientific knowledge supports local work. Other calderas and volcanoes provide examples of unrest, eruption, evacuation, and communication. Yet no other system is exactly the same as Campi Flegrei. Local geology, population density, infrastructure, and history make the region distinct. Lessons from elsewhere must be adapted carefully. The strongest guidance comes from combining global volcanic science with detailed knowledge of the specific caldera. The emergency science interface is therefore an inward layer of responsibility around the hidden volcanic system. Instruments measure the ground, gas, heat, and earthquakes. Scientists interpret patterns and uncertainty. Authorities translate evidence into alert levels, plans, restrictions, and public messages. Communities receive, question, and act on that information. The process remains active even when no eruption occurs. It is a steady practice of caution in a place where the ground itself is monitored because it continues to change. At the deepest point of present knowledge about Campi Flegrei lies uncertainty itself. This uncertainty is not empty. It is bounded by observations, experiments, models, and the volcanic record. Scientists know that the caldera is active. They know that the ground has risen and fallen many times. They know that earthquakes occur within the shallow crust. They know that gases and heat move upward through a hydrothermal system. They know that magma and deep heat have shaped the region through large and small eruptions. What remains uncertain is how these parts connect at a given moment, and how the hidden system will change with time. The inner question begins with pressure. Pressure can rise in magma, gas, steam, or hot water. At Campi Flegrei, more than one source can contribute to the same surface signal. Ground uplift may come from expanding hot fluids, from gas released by magma, from new magma entering deeper storage, or from a combination of these processes. Similar uplift patterns can be produced by different underground arrangements. This means that deformation is real and important, but its cause cannot always be assigned to one process with certainty. Magma adds another layer of uncertainty. The presence of deep magmatic material is supported by the volcanic history, gas chemistry, heat flow, and geophysical studies. Yet the amount of liquid melt, its exact depth, and its ability to move upward remain difficult to measure. A magma body may be mostly crystalline and immobile while still releasing heat and gas. it may contain pockets of melt that are not connected to one another. It may receive new magma from below without immediately creating an eruption path. The difference between stored heat and mobile eruptible magma is central, but it is hidden. Fluids complicate the picture further. The hydrothermal system can amplify, delay, or obscure deeper signals. Gas rising from magma may mix with groundwater, react with rock, and emerge at the surface with changed chemistry. Pressure may build beneath sealed clay-rich layers, and then release through fractures. Steam may expand suddenly in shallow zones. These processes can produce earthquakes, gas changes, and deformation without fresh magma reaching the surface. They can also respond to deeper magmatic input. The boundary between hydrothermal unrest and magmatic unrest is therefore gradual rather than sharp. Timing is the most difficult unknown. Monitoring can show that a system is changing, but it cannot yet determine a precise moment when an eruption will occur. Some volcanoes show accelerating signals before eruption, others show strong unrest and then quiet again. Campi Flegrei has already produced modern unrest without eruption. This record teaches caution. It also prevents simple dismissal. The absence of eruption during earlier unrest does not prove that future unrest will end the same way. The presence of unrest does not prove that eruption is near. Location is also uncertain. In a caldera, future vents are not restricted to one summit. Magma or gas can exploit different fractures depending on stress, pressure, and rock strength. Past eruptions occurred from scattered vents across the caldera. Scientists can estimate areas where vents may be more likely based on past activity and structural patterns, but the exact location of any future vent cannot be known in advance. This uncertainty matters because hazard changes strongly with position. Scale remains uncertain as well. The geological record includes very large eruptions and much smaller events. A future eruption, if one occurs, is not automatically expected to match the largest ancient eruptions, nor can it be assumed to remain small. The most responsible assessment considers a range of plausible scenarios and ties them to monitoring data as conditions evolve. The past provides evidence of capability, not a script. The deepest unknowns are therefore not signs of ignorance alone. They are signs of a natural system with many interacting parts hidden beneath rock, water, and settlement. Campi Flegrei is measured more closely than most volcanoes in the world, yet close measurement does not remove complexity. It reveals it. Each earthquake, gas sample, satellite pass, and field survey adds detail to the inner picture. The picture remains incomplete because the caldera is not a machine with one visible control. It is a heated, fractured, fluid-filled, partly molten region that changes slowly until some parts change quickly. In this inner region of uncertainty, scientific language stays careful. Observations indicate continuing unrest. They indicate pressure changes, shallow fracturing, strong degassing, and persistent heat. They indicate a volcanic system capable of eruption. It remains uncertain whether present activity will lead to eruption, remain non-eruptive, or shift into another pattern. The uncertainty does not make the danger imaginary. It defines the need for monitoring, preparation, and calm attention. The hidden volcano beneath Europe has not simply moved as a single dramatic gesture. Its ground has risen, its rocks have cracked, its gases have changed, its heated fluids have continued to circulate. These movements belong to a caldera with a long history and an active present. Catastrophe is not a certainty written into the next moment. It is a possible outcome within a wider field of hazards, exposures, and unknowns. The inner truth of Campiflegrae is measured in signals that require patience. Beneath the city, the coast, the vents, and the old volcanic layers, the system remains watched because it is alive in geological terms and because its future is still unresolved. The landscape settles back into its ordinary shape. The bay remains open to the sea. The hills keep their old curves. Towns rest on layers of ash, tuff, lava, and sediment, while instruments continue their quiet measurements across roofs, roads, vents, and shorelines. Nothing in the surface view explains the whole system at once. The caldera keeps its history in buried layers and its present state in small changes of height, heat, gas, and motion. Campiflegrae remains a place where knowledge grows slowly. Each observation narrows uncertainty without removing it. The ground may rise or pause, earthquakes may cluster or fade, steam may drift from warm vents, carbon dioxide may pass upward through soil. These signs belong to a volcanic system that is active, complex, and closely watched. The deeper region remains hidden, but not ignored. Rock, water, gas, crystals, and heat continue their slow exchanges beneath the coast. Some processes are measured directly, others are inferred from careful evidence. Science stays with what can be observed and keeps uncertainty in view. It does not turn silence into safety, and it does not turn unrest into certainty. Above the caldera, daily life continues under open sky and changing light. The sea moves against the harbour walls. Buildings stand on old volcanic ground. The hidden system remains part of the landscape, neither still nor fully revealed. Its future stays unresolved, held in patient monitoring, steady preparation, and the quiet limits of present knowledge.